بسم الله الرحمن الرحیم و لا حول ولا قوة الا بالله العلی العظیم حسبنا الله و نعم الوکیل نعم المولا و نعم النصیر. Today we will continue with the last part of this chapter, the stiffness analysis. About stiffness analysis, we would like to find the relation between the position and the force. Stiffness, like a spring stiffness, is defined by the relation between the position and the force. How this comes into the picture in a robotic system? Consider that a serial robot is exerting a force and a torque or a wrench, simply a wrench, to the environment. Now, if this robot is completely rigid, then there is no reflection in terms of any deflection in the joints appearing if it is completely rigid. But usually the robots are not 100% rigid, and it is not very good to have all the joints and lengths very rigid. In the beginning of the design of the robotic manipulators, they try to design the robot as rigid as possible to perform with the minimum error in the positioning because of the fact of stiffness. But after a while, it said that this is not very good because if you would like, because of two reasons. Because if you would like to have a very rigid robot, you should have very bulky and heavy robot. And many robots are used to be quite lightweight. And on the other hand, if the robot is very rigid, then the interaction with the environment would be quite rigid, and if it hits something, since the robot is very rigid, it will destroy. If it hit a wall or it hit a man unintentionally, a person within the environment, it will kill the man because it is very rigid. So the stiffness and controlling the stiffness of the robot is an issue that is in the mind in terms of analysis, in terms of the properties of the robot, and also in terms of the physical component that we use. So it is not rigid in practice, and as we go on, as you see, this KUKA robot is much lighter and than the old version of KUKA version of robots, which are quite heavy and bulky. But the sources of stiffness or compliance, compliance is the inverse of the stiffness. Stiffness is a measure of rigidity. We call it safety or sakhti in Farsi. Compliance is the inverse, narmi, how it can relate that the force and position. The main reason of the main reason of the stiffness could be, first of all, because of the robotic structure. Let me talk about it a bit more detail. If I have a serial manipulator, an articulated manipulator, if I have an articulated manipulator, I put a force in here or a wrench in here, it is quite more possible to have some deflection in the arms. So if I have compared to a parallel robot, if you have a parallel robot, if I have two hands together, then it becomes more stiff. If I put some force in here, the deflection will be reduced. If I have only one hand, it would be much more deflective than if you have two hands all together. So the robot structure, if I have closed loop kinematic chain or open loop or a hybrid kind of thing, how many links we have? The kinematic is RRR or PR. What kind of structure we are using is the main reason that we can have stiffness. Of course, the structure will be by links and joints, defined by the links and joints and how they are appear to each other. So the link itself, just consider the link. It could be rigid or it could be compliant. And I can say we have something in between. We never have a fully rigid link, but the link could be very, very compliant or quite rigid. The joint is as well. The joint itself is also quite possible to be very rigid or quite compliant. I will show you some particular thing for that. So we have compliant link or flexible, we call flexible link manipulators. If the link is too flexible, then there is a wide area of research on the flexible link manipulator. If you have a flexible joint manipulator, there is a wide, quite research items on the control and the modeling of this kind of flexible joint manipulator. And maybe the most important or the main source of compliance in robots are the actuators, sensors, and transmission or transducers, the gearbox, the transmission system, and the force sensor, if you have any force sensor. This is the main cause of the actuator, usually the main source of the compliance, because usually in the robot we intentionally add some flexible joint or element. If we would like to measure a force, we need somehow to put a flexible element that we can measure the force by strain gauges. If you go to the instrumentation part of the robotic manipulator system, you can see that if you would like to measure a force or a torque, a wrench, completely a wrench, you need to have a flexible element. And that flexibility will cause some reduced stiffness or compliance to the system. Also, the transmission, the most significant transmission type that it is used usually in nowadays the robotic manipulators are harmonic drives. And harmonic drive is a fully flexible fully flexible transmission. I'm very sorry about that. Okay, I will talk about that in the next slide a bit on how this could come into picture. But there is also one last point in the structure of the robot which may cause it quite flexible. And this is due to the control structure. We can have a control structure with high gains. It becomes a very stiff robot. You might have a more compliant control structure, like an impedance control or a stiffness control. Then we can, although all the parts might be quite rigid, we can make the robot quite flexible. And if you would like to understand how this will work, consider that you shake hand of course after Corona or before Corona with a very rigid man. If you shake hand with that, your hand will be squeezed so much. This is a stiff environment or stiff hand. But if you shake hand with a kid, you can see that the hand is quite compliant. It is very naturally behaved and more pleasurable in terms of interaction with the human. Consider this part of the system. Now we have a number of joints and the structure. How this flexibility can aggregate to each other and give us a complete stiffness. This is the stiffness analysis that we do. And again, Jacobian matrix becomes very, very important in here, and amazingly distributing to that. Now, among all these parameters, let's consider the actuator and transmission, the main source of the flexibility in the system. As a sample, I am introducing Harmonic Drive. Harmonic Drive is a special design gear system which is performed, the transmission is performed through a flexible element. It has a circular spline, a rigid gear. You can see very, very tiny gears here. And you have a flexible spline. This one, this external element is flexible, it can move. And they are in the radius, this is a bit smaller than that. Either if one or two gears less, it has the one or two less gear than this one. So if you put these two together, it is somehow loose. And we have a wave generator or an elliptic ball bearing. And it is very interesting. When they will put all this together, then this ellipse will make this connection of these gears in terms of an ellipse in here. You can see in this figure, if it comes, okay, you have an ellipse here. I'm sorry. And then when you move to the right, you see this ellipse is moving, and since we have one or two gear less, we move to the left. You move the motor or the wave generator to the right, but this one moves quite backward. You can see again, maybe this figure. Look at that. It goes backward quite effectively. And why harmonic drive is used so much? Because it has a special design. It will give us a very high ratio. You can find a higher ratio, gear ratio of 100 in a very small harmonic drive. This is not very easily done by other means of gear ratios, since you need some different type of gears or a number of gears in a series or in a circular way to do that. But the harmonic drive make it very, very fast and very effective. That's why it's very used much, and unfortunately or fortunately, my PhD thesis was on this special harmonic drive system and the control of harmonic drive system. You can see that there is a flexible element here. So the joint is inherently flexible. You cannot get rid of that. And if you lock the system, if you don't move the system, and put some force on the end effector or wrench on the end effector, this flexibility will provide you some deflection. And how we can design this deflection? We can say, okay, each joint, for example, has a deflection or have a stiffness. If we add a torque to here, there is a deflection Qi, tau I will result in a QR or delta Qi, a small deflection in terms of position. And what is the relation between that? This is the relation between the joint stiffness constant. So if we consider a larger harmonic drive in a larger flex spline, the gear ratio is much better, but the flexibility is higher. The flexibility or the stiffness of the joint is Ki. As much the Ki is large, it becomes rigid. But if it is more compliant, this K is reduced. So it means that by a smaller torque constant, by a smaller affecting torque on the joint, we have the same deflection. So this stiffness constant, like a spring, very simple like a spring. Of course, here we have a revolute joint that we are using. So the revolute joint causes some stiffness in the joint space. Now, we have a number of joints, 1, 2, 3, 2m. We can put all these m together, the taus, and the delta q of each of them all together as a delta q, a vector delta q and delta k. These two are also related to a stiffness matrix. We call it a script k. That is basically the diagonal of these two, all this ki element. And if all of them are using the same harmonic drive or the same structure, then they will be a diagonal unity matrix with a ki or a constant k on top of that. But if there are different harmonic drive, if you are using different k stiffness matrices, this k matrix, which relates the vector tau to the vector q, becomes diagonal. Now, this is not the end of the story, because usually we have, this means that if we put a force or a torque on a particular joint, it is in the joint space. We have a particular deflection on that joint. What about all the system together? How comes the structure comes into the picture? The structure comes into the picture with the Jacobian. It means that now consider that we have a force or a wrench at the end effector. So we have a structure. We are, as we show here, we have a wrench applied to the end effector. How this will be distributed into the joint? We know that this is distributed to the joint by Jacobian. We know that the F and tau is related to each other. Consider everything for now static. We just want to see how is the reflection, the deflection between the force and the position going on. So the force is mapped by Jacobian transpose as a torque to each joint. We have a flexible harmonic drive there. So this will cause some QIs there. And also we know that the delta X and delta Q is related with the Jacobian. Jacobian was both sides, in position and also in torque. Of course, we talked about the Jacobian as the velocities dx or dg to dt related to dq to dt. But since they are very, very small, delta q like dq, we can remove the dt in the denominator and see that these are related to each other, as we consider that for the virtual work approach. So if we use these two relations, now we can put everything into the frame of task space. Instead of delta x, I can say delta x is equal j delta q. So delta q, what about delta q? Each delta q is related to a tau with a k inverse. So the total k inverse would be this for a Jacobian case. And then we have Jacobian k inverse and tau is Jacobian f. So delta x is related to delta f or f with the compliance matrix. The compliance matrix is Jacobian k inverse Jacobian transpose, if it is squared, if this Jacobian is squared. Otherwise, this inverse is not very easily defined. If we have this case, we can define the Jacobian with the compliance matrix, matrix Narmi, and the way how pleasurable this robot can work with the environment, with the human, with the matrix C, which relates the force and deflection in task space. And C is a M by M matrix. M is the number of joints. Jacobian K inverse Jacobian transpose, as we found it in here. Now, if this is the compliance matrix, The inverse of that will give us the stiffness matrix. This is by definition. So if we consider the relation between F and delta X the other way around, this gives us a K matrix. The K matrix is the inverse of that. The inverse would be J minus transpose K J minus 1. And this is a matrix with some inherent problem. It doesn't matter in which frame we are representing that. This matrix has a value. For example, a norm of this will give us the norm of K will give us how stiff is the system. And as the norm of K is large and larger, let's say 10 to the power 6 or something, then the robot is much more stiff, and we can consider it like a rigid robot. But if it is low, if it is 10 to the power 2 or something like that, then the robot is quite flexible or compliant. Not much mathematics here, but the physical concept is very important. And the issue is that we have somehow Jacobian transpose in here. Now consider that all the joints have used the same harmonic drive. Or consider that the KI's are all equal to each other and is equal to K. If this is the case, then we have C is equal K minus 1, Jacobian transpose. Do you remember this? Anybody has some idea about Jacobian transpose? We had this before
the singularity matrix and
the singularity matrix, the manipulability measure. The same thing that we consider there, we consider it here, of course with a gain K minus 1. If we consider it in terms of compliance with a K minus 1, which K minus 1 could be a small value. Since K could be a large value, then K minus 1 could be a small value. This compliance matrix gives you the structure, and this is why we say that the stiffness is structurally dependent on the structure of the system. We call the robot structure important in the analysis of the stiffness, and the reason is because of this JJ transpose. We have individual stiffness at each joint, but they will be aggregated all together by JJ transpose, the same old JJ transpose as before. And we can have the singularity, the thing that you have there, especially the transformation is the ellipsoid. We can have the ellipsoid here as well. So consider this compliance matrix, KK minus 1, and usually if you would like to just imagine or evaluate the concept, we can consider a unity matrix or one value for K to just have the Jacobian transpose. And you'll see that if K is 100 or 10 or something, then you can just have a simple gain to that. The structure will be given by JJ transpose. And since we have the JJ transpose, we could have the same ellipsoid, of course scaled. Why scaled? The scale is coming from this gain that is scaled to it. And if this is not equal to each other, we have a scale in all the direction, in all the element of JJ transpose. We have a weighted JJ transpose. This is the weighted JJ transpose. As you see here, JJ transpose is weighted by K minus 1 general. And if all the K's are equal, just by a number. And we have a scaled ellipsoid or force deflection ellipsoid relation to the system. How much force we are acting to the end effector, how much wrench we are acting to the end effector, and how that this will duplicate or replicate in terms of the deflection in each joint. So this means that we have the same ellipsoid as before, and I hope that you have examined, it was two sessions before that we defined it eigenvalues, eigenvectors, singular values there, and the ellipsoid, the shape that this can become. And if the system becomes singular, instead of having an ellipsoid, we have a cylinder. We have very tall ellipsoid. And this causes some issues in terms of singularity. The same thing can happen here with another approach in terms of the relation between force and deflection. Now, we say that this force ellipsoid or the scaled force ellipsoid can be considered if we have a norm 2 of delta is equal to 1. How much would be the forces? Consider that we would like to have all deflection in the joints equal to 1, all together. What would be the force, in which direction, and the amount of the force, or the wrench, better to say, to the end effector will cause this? How would be the relation between the forces in here? And you can see that this could be completely considered in a system like before. As an example, I brought the same old example that we have there. A 2R manipulator, the most simplest, the simplest possible case with human inspired architecture that L1, L2 is square over 2 and 1. And consider not in a isotropic configuration. You remember that this was isotropic if we had the angle was 3 pi over 4, the same way that we are working with our hand. Consider that theta 2 is equal to pi over 2. We have a perpendicular arm. And if we have a perpendicular arm, and consider K1 and K2 is equal to 1, just to consider the general concept. Of course, this could be 100, could be 1,000, it could be anything, depending on the stiffness that we have at each joint. Then the C, if K1 and K2 is equal 1, the compliance matrix would be, at this configuration, would be JJ transpose at this configuration. And you see that JJ transpose is this. What would be our force reflection? C transpose C. Very similar to J, but a number of higher degree here. You can see that if this is JJ transpose, then C, you can find that this is C, then C transpose C is like that. Of course, the C transpose C, as you see in here, C transpose C, has brought the inheritance of JJ transpose, the eigenvalues and the eigenvector, especially the eigenvector. The eigenvalues are becoming larger. You see here we have 2, here we have 6. So the eigenvalues are becoming larger, but the eigenvectors are the same. If you consider this matrix, as the matrix of analysis, you can see that we have 2 eigenvectors, eigenvalues 11 and 0.3. We have in our position vector something smaller than about 3 or 0.2. But here we have a larger value because we have larger values in here. But the eigenvectors are exactly the same. 1, 1, and minus 1 and 1. It means that in one direction we have the most deflection, in the other direction we have the less direction of deflection. And these are all exactly the same. And what would be the force relation, as you see in here, how we can find the deflection in here with the gain of the singular matrix, exactly like before. These are the eigenvalues. These are the singular values. You just make the square root of them and inverse them. Square root and inverse will become 1.2, and this square root and inverse will be 1.7. And these two gives the gain matrix between the force and the direction that we have. And I have also, again, formulated everything here, as you see, you can see that the relation between delta x and delta f is like that in a 2 norm. So delta x squared would be this, and f squared, just C transpose, we have C transpose C in here, we have 6/8 square root of 2, and this, of course, this number, by linear algebra, we can see we have a matrix multiplied here. So we have an eigenvector. We have 2 components, eigenvector 1, as you see in here, eigenvector 2. We have the force, eigenvalue 1 with the eigenvector 1, eigenvalue 2 with the eigenvector 2. So we have these 2 combination of 2 eigenvalues to each other, and this is a general case. When it would be the maximum value if we are on the maximum eigenvector. When it would be at the minimum value when we are on the minimum eigenvalue. And these are basically defined by G mean 1 over the singular value max and G max on minimum singular value. And you can find this very easily, effectively. You can say, okay, let's see about the first vector and the second vector. If we are only on the first vector, we are the force, the deflection are only on the first the direction. The forces are only on the first direction. Fx is equal to Fy. Then this part would be 0, and the relation between delta x and delta f comes with this value. 11.6, and this is square root of 2 because both of them are equal to each other. This comes here. The inverse, if you want to find here, it comes here, and if you just take the square root, you find 0.292, which is exactly 1 over singular value maximum of the transpose C that we have it in here. So we can find the minimum value of f in x1 direction and the maximum value of f as 1.7 in this direction. And this can be shown in here. So that if you would like to have a quite complete circle deflection, the force, this will become, in this force, if we have forces in this direction, we have the minimum deflection. And if we have force in this direction, we have the maximum deflection. The structure of the robot is somehow in some direction, as you see, 1 and 1 and minus 1 and 1, these two 45 degree and 135 degree. If we act a force on this direction, we have the maximum deflection coming out of here. As you see, the maximum deflection would be 1.7. And if we have on this direction, we have the minimum amount of deflection on this system. And if there is something between these two, we have something between these two. Now, we can consider the singularity, the case that we have before in here. If we become singular, this shape would be very large, like a cylinder. So this means that if we have a cylinder in this direction, to have a force, a value of deflection in this direction, you need a lot of force to be applied to this system. And this is very good. You remember the weightlifting? The weightlifting comes into the structure of singular structure that we have. In the singular structure, when the arm is fully extended, this becomes quite large, and when it becomes quite large, it doesn't really contribute into the deflection of the system. The system doesn't hurt. You can exert a lot of force on singular configuration without becoming compliant or becoming any movement in the system. And the reason is because the force and the position, the Jacobian in the velocity is in forward direction, but in force in the backward direction. The Jacobian transpose was coming into the picture. Anyways, from all these details, the only thing that is important for you is to finding the gains and the directions. The gains can be found very simple by 1 over singular values of this matrix. You don't need all this manipulation to be done every time for every example. The only thing is that you can find what would be the maximum deflection and minimum deflection just simply by 1 over singular value of this compliance matrix that you have in here. So by this means, we have completed the behavior or the inherent properties that a Jacobian can have on the properties of a manipulator. If there is any question, now is the time to ask. If you don't have any question, I can move into the next chapter. We are moving to dynamic chapter. Dynamics is providing some model for the system, the most significant and important part for model-based control schemes that we are giving in the last chapter. And the dynamics show how fast a robot or a human being or a creature in the world can move. And there is how we can work on that. Are you with me? Any posture or something that I can see that you're following me? You have my voice? Everything is fine? Are you not asleep? Hussein is still awake. Zahra is also awake. What about the rest? Yasmin is here. What about Ali? Yeah, Ali, Mehdi. You are following. Okay. Please just speak up. You can just open your microphone and ask some question to have some more interaction with each other. In terms of dynamics, dynamic of robotic manipulator is very, very large area of research. And for electrical engineering students or computer science that we have among us, we used to, it is much better to use the Lagrange formulation. Of course, there are many, many methods to find the dynamics, but since we have limited time and also we would like to have more effective value for here, we will go with the Lagrange formulation. After giving some preliminaries about the basic concept, we give the Lagrange formulation, starting with a very simple motivating example, and then going through the detail. And then after we find the mean, the dynamic formulation, we find the dynamic properties formulation property. These properties is the most significant part of this course, which provide us the avenue how to use the control schemes in here. And then we, in the last part, this is quite interesting, this part, and very, very practical to find, we show that although the system dynamics is quite complicated and nonlinear, if there are some harmonic drive or some gearbox there, then the actuator dynamics becomes very, very effective. We show how this becomes very effective, And then we can use a linear model for the system. And if we have a linear model for the system, then we can have the dynamic calibration. And this part will provide or pave the map for the next chapter. Then in the next chapter, we start with the linear controller, which are much more effective and industrial. And then if we have time, and I hope that we can complete that part, we will go through the nonlinear controller as well. Now, to start with, we go back to the screw, and it is amazing to see that, as we saw that omega, the angular velocity, was along the screw. It is amazing to see that the angular acceleration of a rigid body is also along the screw. Why using Euler angles if the screw is so effective here? And why this is the case, we can prove it by the golden rule. We say that omega dot is d omega over dt, the differentiation of d omega over dt. And we know that omega, as you remember, omega was theta dot times s, theta times dot s. So theta times dot s, the first derivative theta double dot times s, and the second part derivative theta dot s hat dot. And this s hat dot or s dot, as you can see, of course this should be also s hat. As you can see, there's nothing but the golden rule. If you sit on the moving frame, there is no difference here. It would be omega cross s. S dot is omega cross s. This should be s hat. S hat dot is omega cross s hat. And if you see here, omega cross s hat, omega and s are all together, along together, are on the same line. So this part would be 0 because of the screw representation. No, this is only true for the screw representation, not for other representation. And omega dot is equal to theta double dot times s. It means that omega dot is also on the same direction as omega dot. So this is a physical vector in the space. If you can measure the velocity, angular velocity, if you can find the angular velocity vector in the space, you have found the screw axis. If you can find the angular acceleration axis, as you see also again, you have found the a screw axis in here. And a screw axis can be found either by the angular position, motion, or velocity, or acceleration. All of them are all together along one line. Of course, we start with the rotation matrix and found it, but this is a physical property there. And it is very interesting because of this special golden rule, we can prove that everything is, very simply we can prove that everything is along each other. Please just ask me any question and interrupt me if you have some question to, don't go so fast. Now, if we have the angular acceleration, we can have angular linear acceleration of a point here. Again, if you have a point in here, and we would like to find the acceleration here. Again, I don't give any mechanical detail. I just use the golden rule. Very simple golden rule. As we did in the velocity, to find the velocity, you saw that we differentiate from the position. To find the acceleration, we differentiate from the velocity term. You remember that we have three different velocity terms here, which was the velocity of point P is the velocity of the origin of the frame, VOB, with respect to A. The velocity of point P with respect to this, the relative velocity, which is multiplied by RB to A, is just transformed to frame A. We find the relative velocity and add it to here, and then omega cross this point. omega cross the position as we have if this point is not embedded into the system. We have these three terms for the general velocity of a point P. Now, if we would like to find the acceleration, we simply differentiate that with the time. Differentiation of this would be this. Differentiation of this term, we have two parts. This times the derivative of that, time derivative of that is this. This was the relative velocity. Here is the relative acceleration. Very simple. You don't need any sophisticated dynamic tool. Now the other part is, I will give you this one here. Now this, the derivative of this times the velocity. A derivative of r, you know that the derivative of r is omega cross r. We can see omega cross r this term. Of course, these two, one of them is because of that. The second one comes in here. Now we have here a three term, and we would like to get the derivative. So we have three terms here. First, just the derivative of this times this, you can see. Then, derivative of this times this, and derivative of RB is omega cross R. You can see it was omega cross R times B. And finally, the derivative of this. Then to we have a relative position here. The derivative of that gives us the relative velocity. If one term comes from here, these two, we have omega cross R times the derivative of that. It is amazing that these two becomes together, and we have only 5 terms in here. It's not good to say only. We have all 5 terms. We have a lot of terms for the acceleration of a point. Both of the two of them are very important and very sophisticated. In general, this one, omega cross omega, we have omega squared, something with omega squared. We call it centrifugal force or centrifugal acceleration. شتاب گریز از مرکز یا نیروی جانب مرکز in you have to learn in different courses. Omega cross omega. We didn't define them. We just used the golden rule to find that. And also the other part, which is 2 times omega cross V. Omega cross V, multiplication of omega and V together is the Coriolis term. This is also, both of them are somehow nonlinear because we are multiplying 2 terms to each other. Of course, the first terms is the acceleration of this point, and this is the relative acceleration. It is quite easy, and this is the angular acceleration. So these 3 terms becomes directly, these 2 terms becomes indirect, but they are very important. And we have in the gyroscopic effect, these 2 terms are becoming more important if we have higher speed. If we have omegas becomes large, then we have these 2 terms becomes very effective. Now, at the final point in here, if this point P is embedded in the system, as we have usually in our robotic case, the point that we are considering is either center of mass or the joint point. If this point is embedded in that, then the relative velocity is equal to 0, and also the angular velocity, the relative acceleration is also 0. These 2 terms become 0, so we don't have these 2 terms, and the acceleration becomes only for the 1, 2, and the 1, 3, and 4th component. These, the 2nd and the 5th component becomes equal to 0. Of course, we don't use that in Lagrange that much, and that's why the life becomes easier if you consider using If you would like to find the acceleration, you need to do that. But in Lagrange, we just bypass this method, and then we can go to that to define that. The second thing which we should define, of course, for electrical students, not mechanical students. The mechanical students are quite familiar with that, but the electrical student need to know also the mass properties. In mass properties, we have to define three important things. First, the definition of the mass, which is very hard in terms of everybody knows what is mass, but if you would like to define it, it is becoming quite difficult. The mass is something which provide you inertia to the motion, or reluctant to the motion. It is quite hard to say, but the bulky way of that. So to find the mass, we can find a particular particle, a very tiny part of the very beautiful peer, as you see here, and find the mass of that, and then integrate over all the volume of that. And we call, if we have the density rho and the volume dV for this particular very tiny m, we have dm, tiny mass of the system. Dm is equal to rho dV, and the mass of the system is the integral of that over rho dV. And this is exactly the same thing that we can weigh with the gravity, and we can weigh it with a mass measuring system. But this is, of course, you are familiar with the mass. We are just considering it into piecewise. But center of mass is very, very important for our analysis. Where is the center of mass? The center of mass is a point in the system where this body can be balanced about it. If you have a long thing and you have a point there that you can balance the system, this is the center of mass. Of course, physically. In terms of mathematical displacement, since that the point that m times that point, the vector center of mass is a vector, is a position, is a point here, as you see, for example, here, this is almost the center of the geometrical center of the body, if the body is provided with one property, everything is homogeneous. If this is the center of mass, the mass of the system times this center of mass gives the whole mass of the system by, as you see, the mass of system by P. The position here, P times dm, at each point, if you integrate it, gives you a position P times m. You know that the integral of rho dV over the volume is m. M Pc is equal to m pi, or mi pi. If we have here a dm and we have p, if we multiply that and integrate it all together, then we can find the center of mass as in here, mpc, or pc is equal 1 over m, the integral of p, the vector p, times rho dv, where p denotes the position of the tiny mass dm in the frame C. Of course, this point is very important because it is the center of attention of us. And we usually put, if you would like to find the motion of the system, we put a moving platform on this particular point. We have a robotic system, many links. Each link has a center point, and we put basically a rotation matrix or a frame where not at each particular point we put it on frame C. We call it C, center of mass, and we use the C notation in here. So this is the second important thing that we require. The third one is the inertia against angular motion, which we call it the moment of inertia. The moment of inertia is a long story. It has many different issues, but for you as a control student or electrical engineering student, you are familiar with the matrices, so it is quite easy to understand it some other ways. We define the inertia matrix. We don't call it matrix in practice. We call it tensor because it has some mass properties, but it is actually a matrix. We call it a matrix. It is like a matrix that should be applied to the angular velocity. So this matrix has different, it has some diagonal values, ixx, iyy, izz. We call this matrix with respect to a frame as before. Of course, this is frame dependent. We are considering the moment of inertia of this body with respect to frame A. And as you see, Ixx gives you the y2 plus z2 rho dv. It says that how far, what is the radius of this point with respect to the x frame? If you consider the x frame as the center of mass, find the radius. The radius of this point is x2 plus y2, radius squared, r2. This R, the place that we are using, how far it is from this point of rotation. Consider that you are considering a rotation here, and we would like to see how far, how hard it is to rotate it. So that as this rotation becomes larger, the radius becomes larger, the R2, we call it R2 with respect to X, Y2 plus Z2. And the same thing for IYY, the radius with respect to the frame Y, which will be somehow X2 plus Y2 of this particular point. And the same thing for ZZ, which will be X2 plus Y2. And we should consider that, integrate everything all together. Now, if you consider the dimension of I, what would be the dimension? Here we have a dimension of a mass, like kilogram, and here we have an integration of R2. So we have kilogram meter square, something which has the mass and R2, a radius squared embedded in here. This gives the diagonal part of it, and also the off-diagonal matrices are just also symmetric. As you can see, this is equal to this, Ixy is equal to Iyx, which is minus xy rho dv as defined in here. So it is a hell of a job if you would like to find the mass matrix by this integration. And also the mass of the system is also very difficult. If you would like to find the mass of matrix like this, of course we don't find the mass by this, we just put it on the scale and get the mass of the system. But the moment of inertia is not very easy to do that. And you as an electrical engineer never do that by integration. You use either the books that you use or the tables that are around here available on the web, or use the softwares to find that, or we will give you the mass properties. You know, if we have a matrix like that, if this is a general matrix, not diagonal matrix, any general matrix, you know by modern control, that any matrix can be represented, any matrix A can be represented into a diagonal form. We can put any matrix into the diagonal form by using the eigenvalue, by a homogeneous transformation that is found by the vector of the system, of the eigenvector of the matrix. So this has some eigenvectors. And if you just use the homogeneous transformation, we can show that there is a particular, completely particular frame. Here the frame is out of the system. If we can bring the frame somehow in the within the system, that the system becomes symmetric about that, then the moment of inertia becomes symmetric. The off-diagonal terms become zero, and these on diagonals are all positive because we have positive mass. Usually we don't have negative mass in classical dynamics. So the principal axis, if you can find from the eigenvectors of the mass matrix, as I mentioned, for the control people are quite easy. And physically, this means the axis of symmetry of the system. And usually this is given in the books. I just want to show you one of the, you usually use these tables. I provide you any dynamic book that you can use. For example, the Merriam book, which is very, very well attributed here. You can find Appendix D of that, or you can find the software, CAD software that we usually use, the SolidWorks or other AutoCAD or SolidWorks or other CAD version. If you design something, you can easily find the moment of inertia of that. For example, here, since we would like to see, if we have a circular cylinder shell, a robotic link could be either hollow. As you see a circular cylinder, you can find IXX, IXY, and IZZ like here, and the point of symmetry can be found in here. From this XYZ, as you see, XYZ is considered in a way that is somehow symmetric. Of course, this when we have cylinder, it is not completely symmetric, and we have IXX available, IXX and IZZ available. And then if you would like also to find axis here, the IXS is also given to that. You can find if the cylinder is not hollow, it is completely, then here you will find, as you see, 1/2, but when you go further, sorry, it goes 1/4 if this is not hollow. It is like that. Or if you have a rectangular, then IXS are given like this. For this particular axis, or for this particular axis, this integration or integral has been founded here. Or if you have a sphere or a hemisphere, for sphere about the center point, just we have IZZ, because the other ones are symmetric. IXX and IYY is all symmetric, and then you can find IZZ in here. This is usually we use a slender bar. Usually we consider the length of a robot. If it is not given to you, of course we will give everything to you, but if it is not given to you, we use a slender ball. We consider that we have a bar with length L, which is quite slender. This is not like a cylinder with radius R. And this is very simple model for the system. 1/12 ml square is in x direction. X and y is equal to each other. And in z direction, it would be equal to 0 because there is no radius around that. And Iyy, if you consider it at the beginning of it, it would be 1/3 ml square. So if you just remember this one, we might use that in future, but the rest should be considered in the future. Now, the last thing I would like to tell you in here, only 2 slides. The last thing is, if we have, as you saw in the tables, we have the moment of inertia in C frame, usually at the center of mass, like what we have in here. This is the center of mass, and the moment of inertia is given. Then how we can use it in any other frame? If we have it in here, we would like to have it in here. We have to find 2 theorems here. We call it the inertia matrix transformation, either pure translation or pure rotation. If we just move it with a frame which is quite translated from here to here, then this formula is being used. This is given in here. This is very vector-based, very concise and nice way to do it. But usually we consider it. These are easily to find that. You say Ixx. Consider that the X frame is moved from here to here with a Yx and X. As you see, Yc and Zc. The distance between these 2 frames is Y and C. And since Ixx was only, as you remember here, Ixx was only dependent on to Y and Z, when you make a parallelogram, the mass of the system times this radius that you have extended it will add to the C value to find Ixx. Anyways, by using these parallelogram or parallel axis theorem, you can find any moment of inertia from any point to any other point. And if you have only pure rotation, you don't have any translation, and you have all pure rotation, note that this is the most used version that we use. If we have I with respect to the C, frame C, and I would like to find it in with respect to frame A, any other frame, which is only rotated, you know, not translation. The translation is here, the rotation is here. We usually need to do that, and this comes with RCA from left multiplied and RCA transpose, or RAC, the inverse of that, from right multiplication, and then you can find I with respect to these 2 forms. Finally, we need maybe to find the linear momentum, angular momentum, and kinetic energy. This is the most important. We use only this word in Lagrange. But here you see that the linear momentum of a system then is given by m times v, but the velocity of which point of this, we get the momentum of this system, is the mass of the system times the velocity of that. Velocity of which point, because we have at each point we have different velocity. Velocity of the center of mass. We call it the linear momentum, like this. Angular momentum is very similar to that. We say that we have the moment of inertia times the angular velocity. The angular velocity of the whole thing is the same, but moment of inertia of which point or along which point we call moment of inertia about the center of mass. This is very important. The most important point in here is this C point here. So that if you would like to find the angular momentum or linear momentum, you should have considered about center of mass. And what about kinetic energy? The last part, again, we use this one and this one. The kinetic energy of a system is composed of two parts. You should learn that very, very well. The kinetic energy is defined again in vector form like that, but we call it the kinetic energy is defined by the momentum, linear momentum, dot multiplied by V, one half VC dot GC, where GC is like this, or call it 1/2 MVC dot VC, 1/2 MV squared. Of course, V squared in a vector form to find it for a general 3D motion. And plus 1/2 omega dot HC, which HC is given here, 1/2 omega dot I dot omega, 1/2 I omega squared. The velocity would be 1/2 mv squared plus 1/2 I omega squared, make it in short. And in general, we should find VC, GC, and HC as we defined in here. We need the moment of inertia and the mass matrix being well done in here. So I will stop it here and hopefully will give you the Lagrange formulation for the next semester. As you see, we are approaching to the end of the class, and the most significant topic that we covered in the chapter 4 was the Jacobian and its properties, which gives a lot of physical meaning to us. Here we are moving toward the control, and we have to work on the control. So please kindly follow me. Don't leave the assignment for late assignment, or you should follow me to considering having a fruitful final conclusion for the course. If there is any question, please. Today is the due to your assignment, and Wednesday would be the due to your project. Somebody has opened the, yeah. Hossein, please.
Yes, I have very general question. It's not particular for this chapter. A part of it particular to this chapter. My question is, how does understanding understanding of the robot from a physical perspective and imagining the movement of the robot may lead to accurate studies? And is it sufficient to only rely on the mathematical procedure from your experience? If we can return to, this question is, I inspired this question from slide 50 you gave in the chapter 4, when the athlete was trying to
lift,
trying to lift the weight. Before entering to the mathematical procedure, yes, here.
Does it go through that? Does it like to go there?
Yes. Before entering to the mathematical procedure, we see that the lifting force is okay. The lifting force and the weight force has physically the lifting force and the weight force are aligned. Physically, we can conclude that this is the maximum or is the optimal configuration that we may lift it this way. Also, it can be concluded that from the stiffness, it is the most safer, or it's the safest configuration for the joints of the athletes to move this, or to lift this weight.
Mm-hmm.
So it is the most
it is optimal.
The optimal configuration for the stiffness.
Mm-hmm. Okay.
Okay. What about my first question?
You know, I answer your question in another way. You know, you should look, this is not, your question as I understood was, is it enough to go and inspect through the nature and find what is going on to say that this is an optimal case or not? I re-examine it in the other way. Say that yes, you should go and look into the nature, but you should also analyze it mathematically. This becomes if you didn't have the notation of Jacobian there. If we couldn't relate this optimal point to Jacobian, it was a very good observation. And it is, many athletes don't know anything about Jacobian. Of course, their coach should know, but they don't know about that. There is a very good observation, but when you would like to bring this into the design procedure, you need to give rigorous mathematical representation to do that. And the robotics is very interesting in this sense, that you have known a lot of linear algebra, you know a lot of mathematics, but you usually doesn't have the sense, the physical sense. Robotics provide you with this sort of physical sense. And that's why so many students, electrical, mechanical students, are very keen to do the robotic competitions and build their robot, because they understand, they see and they feel how this works. But, you know, again, I say, this is, if I didn't know that the Jacobian is related to this giraffe, stretching the neck, that won't be that pleasurable. But if you know that this is somehow getting to the workspace of the robot can be found not only by the forward kinematic, or inverse kinematic, but also from the Jacobian, when the singularity of Jacobian is related to the forward kinematics. These are the issues that is important in my opinion. And I think that a very good engineer or a very good scientist is the one who can relate these two objects to each other. And more than that, Einstein says, Albert Einstein says, if you know something, then you can explain it very simple. If you can understand that relation, and then you can represent that to the general audience quite simple, you are a good scientist.
Thank you.
You're welcome. Zahra, you don't have any question?
Not actually anything.
Not today. Very good. The only thing I would like to say is next week we have Sunday and Tuesday. Tuesday is a holiday, national holiday. Sunday is the night after Ahya, and we cannot start at 7:30. For next Sunday, the only one time, the class would be postponed to, if you don't mind, 12 to 1:30 a.m. Tehran time. Instead of 7:30, we go to 12 at noon. We start at noon and end at 1:30. I will write it in your website that everybody knows, but please be concerned about that. and hopefully we would have our midterm exam assigned next week or the next session to be after the month of Ramadan, just exactly after the month of Ramadan, when you have given the second part of the assignment given back to me. Thank you very much and take care of yourself. Please contribute more in the class. It is not very good for me to be the only speaker in the class, and I hope that everybody can contribute to have a better performance in the class. Thank you very much and goodbye.